In this lesson, we're going to start looking at uranium enrichment. That is, how do we get from that naturally occurring, 0.71% uranium-235 up to something that we could use in a nuclear weapon, which is around 90%. Now, we're going to briefly talk about the different methods that have been used in order to enrich uranium, but we're more going to focus on how does it actually occur? Like, what is the mechanism behind getting from that low initial enrichment to something higher? Now, the methods that we're going to look at in some of the subsequent lessons are electromagnetic isotope separation, which is called EMIS. We're going to look at gaseous diffusion. We're going to look at gaseous centrifuges, something called aerodynamic nozzle, and a variation on that, which is the helicon vortex. Then we're going to take a look at laser enrichment methods, both on the atomic scale and on the molecular scale. Now, I've put chemical separation in here because there does exist two different processes, one developed in Japan, one developed in France, that are purely chemical and can be used to enrich uranium. However, neither of these processes has ever been used on a commercial scale, and I'm not going to put a lot of time into talking about them, but I will discuss a couple of the specifics again a little later in the course. So, uranium enrichment. The thing that you need to keep in mind when talking about uranium enrichment, regardless of what technology that you're using, is that whatever it is, you have to have the same amount of stuff going in as you do coming out. So as the slide says, it's all about that mass. So what we have here is a super generic representation of something that can perform enrichment. For now, it's just a black box. It doesn't matter what's actually occurring. It's just, this is a very generic description. So we have something. We feed our initial uranium, which has some kind of enrichment, usually natural. We feed it into the box, and then we have two outlets of the box. One is the product stream, which has a higher enrichment than we started with, and the other is the waste stream, which has a lower enrichment than what we started with. And they all have to add up. So if I have 10 kilograms of, say, natural uranium going in, I must have a combination between the product and the waste outputs to equal that same 10 kilograms. Now, in the real world, there's a little bit of loss. Stuff gets stuck in pipes. Stuff gets plated into different parts of the whatever the enrichment technology is. But generally speaking, what goes in must come out. Now, the equations that govern this are very simple. So just as a broad general overview, F, which is feed, is equal to product plus waste. Now that's for the total mass that goes in and comes out. But more specifically, when talking about uranium enrichment, it's the same thing with how much uranium-235 goes into the system must be the same as how much comes out of the system. So if we take a look at that 10 kilogram example, say that only 700 grams of that is uranium-235 that's coming in. Well, then if we look at our output, our product, and our waste, we have to come up with the same 700 grams. Now, if this is a really efficient way of separating our uranium-235 from our 238, we may get 600 grams coming out of the product stream, which means we would only get 100 grams coming out in the waste stream. At the same time, though, we're also going to have the amount of uranium-238 also going in that product stream and going in that waste stream. And we would be, if we have 600 grams of uranium-235 going into our output stream, that has to be compensated by 600 grams of uranium-238 being shifted to the waste stream, or something very similar to that. So it's not just the total mass, but it's the mass of each of the pieces, right? So we have to have the same amount of uranium-238 coming out both sides and the same uranium-235 coming out both sides. And that's all that this diagram is showing. Now, when I talk about here in a little bit, the percentage of uranium-235, either in an individual single piece of technology, like is shown in this black box, or a cascade, which is a whole bunch of these all put together, usually it's denoted by the variable X, and the subscript on the X tells you whether it's the percentage in the feed, the product, or the waste. Now, it'll be a lowercase x if we're talking about an individual unit for enrichment, be it a singular gas centrifuge or a singular gaseous diffusion chamber, right? That's going to be a lowercase f that denotes, lowercase x that denotes what percentage of 235 it is. When we're talking about cascade values, we're going to use an uppercase x in order to delineate the two, because they are very different in how we're going to use them in a couple of calculations. So if it's a single stage or a single unit, it's lowercase. If it's for an entire cascade, it's uppercase. Now, there are two things on this particular slide. There's a separation factor and there's an enrichment factor. And the separation factor is mostly used for things that aren't that great at separating, which don't provide a large increase in a single unit. And these are the ones that we're going to talk about: gaseous diffusion, gaseous centrifuge, aerodynamic separation, and also chemical separation. They're not super great at, like an individual one, they're not super great at separating out uranium-235 from 238. The other one is something called the enrichment factor, and this is for processes that are extremely good at separating out our uranium-235 from our uranium-238. And these are, in their entirety, electromagnetic separation, or EMIS, and the two laser methods. So let's dig into the first one, which is our separation factor. Now we have two variables, lowercase x, right, with a subscript P and a subscript W. So this means that our separation factor is entirely determined or consists of the difference between the amount of enrichment coming out in the product, or the percentage coming out in the product, and versus the percentage coming out in the waste. It doesn't even matter how much we started with, right? This factor only considers the difference between the product and the waste. Now you're probably saying to yourself, well, okay, I get it. I can do some math. So if you gave me the fraction in the product and the fraction in the waste, I could tell you what the separation value alpha is. Well, no, not really. It doesn't quite work that way. The separation factor alpha is determined by whatever technology you're using. So if you're using a gaseous centrifuge of a specific design, it will have a set alpha, and it's not something you can change. In the same vein, if you had a specific gaseous diffusion chamber, it will have an alpha that is determined purely by what it is, by the parameters of that diffusion chamber. So your alpha is not something that you can change the value, or you can say, all right, well, if I want this much in my product and I want this much in my waste, then I need something, that I'm going to have an alpha of, whatever. No, the alpha is already set, and then you can only basically look at the difference in the values between your product and your waste stream. Hopefully that's a little more clear than it sounds. So if I were to give you, for an example, if I were to give you an alpha of value of 1.5, and then I were to give you a product percentage of, say, I don't know, 20%, you could then determine what should be the waste percentage. But I cannot give you a product percentage and a waste percentage and magically you come up with something that has an alpha that's the desired value. Okay. Similarly, if we look at the enrichment values, These are very specific to whatever it is you're using. You can think of it as these separation factors and enrichment factors as a physical limitation of the technology you're using. Okay? And we'll talk a little bit more about alphas and how do we even come up with them for these different types of technologies. So for the enrichment factor, it's the difference between the product and the feed. So what we're ending up with versus what did we start with. Now the reason that we have both of these equations is if we had, say, something that was super good at separating out the uranium-235 from the uranium-238. So say that we were able to get in our product stream 95%. Okay, and our waste stream, we were able to not really have any in our waste stream, extremely low. So maybe 0.02%. If we start plugging those numbers in, we start to see that separation value of alpha, right? It starts to blow up. It becomes extremely large to the point where it doesn't really have any meaning anymore. So some technologies that are extremely good at separating and having that big difference between the product and the waste streams, the number that we would be able to come up with, or the number that's inherent to that technology, wouldn't really be all that useful. So instead of comparing the product to the waste, we compare the product to what did we put it in the first place, and then we don't end up with some gigantic number with no meaning. That's the whole reason why we have a separation value, a separation factor versus an enrichment factor. And enrichment factor, for all of the calculations we're going to do for the uranium enrichment, we're not even going to look at that. Because again, it's only 3 different processes that can do it, and none of those processes are really are commercially used or readily available for the most part. So that's looking at individual units, like an individual centrifuge. So if an individual centrifuge is only capable of a particular separation, which isn't very good, then you may ask a question, well, then how do we go from natural uranium all the way up to something like 90% if we can't do it with a single centrifuge? Well, we put them all together in a row and we connect them all. And that's something that's called a cascade. A cascade, I have a little graph here, a little figure here on the right-hand side. This is kind of a very crude depiction of what a cascade would be. So let's say that we have these 7 different centrifuges that are all the same, so they all enrich to, whatever their limitation is. So each one can enrich by, we'll say, 0.5%. So our feed comes in here to this middle one, right? And it enriches to 0.5%. That 0.5% is then put up into number 5. Now that one takes that 0.5% and increases it to 0.75%. Okay, that 0.75% then goes up to number 6, which then again increases it by that same amount. And then that goes all the way up to the last one, which increases it again by that same amount. And then by adding up all of those different steps of enrichment, we can come up with a total enrichment from starting with the feed and going all the way up to the product. Similarly, the waste streams also go down, get fed into another unit so that they can hopefully extract more of that uranium-235 before we throw it away in the waste stream. And that continues down to number 3, number 2, and number 1 until now we have a waste stream that has a particular percentage of uranium-235 in it. So we have these 3 different numbers, which is our fraction or amount of uranium-235. Sorry about that. We have XP, XF, and XW. But because this is a cascade, these are going to be capitalized because these are numbers we can set in order to achieve what we want out of the cascade. So unlike with the individual units, which are limited by their whatever technology we're using, a cascade is not bound by that because we can just put enough of them in a row in order to achieve the desired outputs. So how do we calculate the number of these stages or individual units that we're all putting together, all connected together, are we going to need for whatever our desired outputs are given a particular input? So the number of stages is a function of the waste stream from the cascade, the product stream from the cascade, and here's our alpha value, which is how good is this particular technology in separating stuff out. So we have to know what we're using, and then we can say what we want coming out of the top and coming out of the bottom. And then this equation will tell us, all right, well, here's how many you need to hook together. As you can see in this figure, so 1 to 1 to 1 to 1. Now that's the total number of stages. But you may also want to know how many stages are below our initial input and how many stages are above the initial input. Now the stages below the initial input are called the stripping stages. Okay, so their job is to pull out as much uranium-235 as possible before we dump before our waste stream, before we dump what we don't want, which is normally mostly uranium-238. So they're called stripping because they're stripping that uranium-235 out of the waste. Above where our feed is coming in right here, they're called enriching stages because we're concentrating the uranium-235 that we do want more and more as we move up the cascade. So to calculate the number of stripping sections, we need to know the waste and the feed. So what's the difference between what we started with and what's coming out the bottom that we're just going to throw away? We also need to know, again, what our enrichment technology is. So in this case, we're using this variable beta. And beta is simply the square root of alpha, which is our separation factor. So if you have the total number of stages that you're going to need, and you know how many stripping stages that you're going to have, you just subtract the stripping from the total number of stages and you get the number of enriching stages. Now, something I needed to point out is that this is for what's called an idealized cascade. So this is based off of some math and some physics. It does vary from this a bit in the real world, again, because there are certain factors that are not taken into account. But for all intents and purposes for this class, we're just going to say that the idealized cascade values that we're coming up with, they're close enough. And then finally, this particular figure, this shows what an actual cascade looks like. And it's got this kind of funky looking diamond shape. And the reason for this is that as we go from our starting feed, which is right here, as we start moving up the cascade and we're enriching in uranium-235, remember our feed is probably mostly uranium-238. So the mass, the total mass that's moving through the cascade is going to get less and less as we get up higher and higher towards the enrichment value that we want, because we're throwing away most of the material. We're throwing away most of the uranium-238. So each one of these lines of rectangles is a single stage. But each rectangle itself is one individual unit. So what you can think of this as, if I wanted to move X number of kilograms through stage number 1, I would need whatever this is. This is maybe 20 something units of centrifuges. But their output, because I'm throwing away again a bit of the mass that we're starting with, their output isn't going to need nearly as many stages in the next step, or nearly as many units in the next step or stage. So we can reduce the number while still having the same amount of enrichment. But again, we're still throwing away more than half of our material. And then so as we move up the cascade, we're throwing away more and more. We're keeping less and less. So we need fewer and fewer individual units in each stage to accomplish the job that we're setting out to do. And then the stripping section kind of is sort of the same way, because as we have less and less uranium-235 that we can pull out, we need less and less individual units in each stage to accomplish the job. Hopefully that makes sense. So in the next few lessons, we're going to look into individual enrichment methods. Again, EMIS, gaseous diffusion, centrifuge, and laser-based methods, along with a couple others.